problem number 10a, we're asked to evaluate this limit as x approaches 0 of sine of 6x over x times secant of 8x. So to answer this question, there's one particular identity that you must know to answer this, which is that if you have the limit as x, or when you choose a different variable for the equation here, as theta goes to 0 of sine theta over theta, this limit is always equal to 1. So that is essential for you to answer to this problem. So we kind of have that here. So what I'm going to do first is break this into two pieces. So we have the limit of a product of two things, sine of 6x divided by x, and 1 over secant of 8x. But remember that 1 over secant is just cosine, because cosine and secant are reciprocals. So this is just multiplying by cosine of 8x. So as you can see here, we have something that looks kind of like this right here, and then we just have a cosine of 8x. So we can't apply this limit right away because our what we're taking the sine of and what's in the denominator are not the same thing. But we could easily do that by just multiplying the numerator and denominator of this by 6. So what I'm going to write instead is 6 sine of 6x over 6x. So I just multiply the numerator and denominator here by 6 times cosine of 8x. So now I can use my limit identity that I had written down here. So this part right here, the sine of 6x over 6x as x approaches 0, that goes to 1 because what you're taking the sine of and what are on the denominator are the same, and that term is going to 0. So keep in mind, it's not important that x is going to 0. It's important that whatever you're doing is going to 0. But 6x is going to 0 when x goes to 0. So this part here is just 1. So essentially I'm going to cross that out because you're just multiplying it by the 6 that's left over. And now we're just taking the limit as x approaches 0 of 6 cosine of 8x. Because we still have the cosine of 8x over there. But at this point, we don't need to do anything else tricky. We can just plug in 0 because the cosine of 0 is 1. So then we get that this limit is just 6 because it's 6 times 1. So knowing this trig limit identity right here is key to answering this problem and most of the rest of the ones in this section. In problem 10b, we're evaluating another trig limit. In this case, we're still going to need to know the identity we used in problem part A, which is the limit as theta goes to 0 of sine theta over theta is equal to 1. So this limit is going to be very important to us in answering this problem. So here we have that a limit sine of 8x, sine squared of 8x over tan squared of x. So we can see we don't really have this form in the problem just yet. We need to create that out of messing with the algebra. So what I'm going to do first is, since the limit operation applies through all operations in math, addition, subtraction, exponentiation, I'm going to say that this is the same thing as if you did the limit as x approaches 0 of sine 8x over tan x squared. Since both top and bottom are squared, I'm just going to say the whole thing is squared, and then I can just do the limit of sine 8x over tan x, and whatever answer I get, I just square it. So instead, I'm going to be focusing on the following. Just the limit of sine 8x over tan x. Okay, so now we need to try to get this trig limit identity out of this. So we can do that. We're just going to have to do, again, some tricky things in our algebra. So first of all, I'm going to change the tangent to sine over cosine. So our next step, we're taking the limit as x approaches 0 of sine 8x divided by sine x over cosine x. So I just changed the tangent into sine and cosine. And you can see now, to get this limit out, there has to be, whatever you're taking the sine of has to be divided into that sine term. Now we have a sine on the numerator and a sine on the denominator, so the easiest way to go about this is to say I'm going to multiply both the numerator and the denominator by 1 over x. So the reason I did that is because look what happens afterward. You get sine 8x over x divided by sine x divided by x cosine of x. Now we're really close to having this identity present in our problem. So as you can see here, we actually do have a sine x over x already as x goes to 0. So that would actually cancel out to give us 1. So we still have a 1 over cosine on the bottom. But cosine of 0 is also 1. So our numerator, or our denominator, our entire denominator here essentially is just 1 and it all goes away. So we're just dealing with sine 8x over x. And this is something we just did a similar thing in part A of this problem. To use this identity, what you're taking the sine of and what's on the bottom have to match. But we could do that really simply here by just multiplying by 8, top and bottom. Remember, you can do that because you're not changing the answer as long as you multiply both the numerator and denominator. And now you can see here, sine 8x over 8x, this term that I just circled there, that is equal to 1 by this limit identity. So that goes away too. The only thing that I'm left with in this entire thing is 8. However, remember that whatever we got during this, the work on this limit, we have to square it to get our final answer. So our final answer here is 8 squared, which is 64. Again, the key to answering this problem, though, is knowing that trig limit identity and how to apply it. Problem number 10c, another trig limit here, but this one's a little bit more of a trick question than the others, because this one you actually don't even need to know any limit identities or really do any work on at all, because this is an example of when direct substitution, not giving you an indeterminate form, means that is the answer. In other words, we can just plug in pi for theta here, and we get a definite, concrete number. We don't get any sort of indeterminate form, so that's just the answer. So if we plug in pi for theta, this would be equivalent to the sine of pi over pi plus the tangent of pi. But this is pretty simple to answer because the sine of pi and the tangent of pi are both 0. So this becomes just 0 over pi, which is 0. Don't have to do any work here, again, because if you can plug in the part of the limit, or what the limit is going to, and you plug that in for the variable, and you get an answer, then that is simply the limit, and that's all we have to do in this problem. In problem letter D, 10D, we have the same function that was in problem letter C, except now our limit is approaching a different value, and in this case it's not going to be as simple. Because you can see here, if theta was going to 0, we get a 0 over 0 indeterminate form here. We would not be able to answer this question, or not by direct substitution. There's something that we need to do to simplify it. But as is the case with most of the problems here under this trig limit section, we need to try to get our identity out of it, our sine theta divided by theta identity. And we can do that really simply here by doing a trick that we did in one of the previous problems. We're going to multiply the numerator and denominator by 1 divided by theta. Let me write that like this. So we're multiplying the numerator and denominator by 1 divided by theta, dividing the numerator and denominator by theta. So this is going to do a world of good for us in making this problem easier. We're going to get sine theta over theta on the numerator. On the denominator, our first term is going to be theta over theta, which is just 1. And then we get tan theta over theta. So now we're sitting in pretty good shape because we can apply our trig limit identity to everything here. First of all, we don't need to worry about this term anymore because it just became a constant. But sine theta over theta, as theta goes to 0, that is our trig limit identity. That is equal to 1. Similarly, tan theta over theta is also equal to 1. And you can check that because tan is sine over cosine, so the sine theta over theta part becomes 1, and cosine of 0 is always 1. So tan theta over theta is a similar limit identity that always holds. And that's also equal to 1. So as you can see, what we got here is 1 over 1 plus 1. In other words, 1/2. So again, when you get these trig limit problems, your goal should always be to try to get one of your limit identities that you know to be present in the original equation, even if it's not already there. So in this case, we didn't have our limit identity present by just doing a simple algebra step, dividing both the numerator and denominator by theta. We're able to get our identity to come out, and then it becomes very simple from there. For problem 10 part E, again another trig limit. In this case, we're going to have to use our same identity, but we're going to have to apply it in a slightly different way. So as you can see here with this problem, if you try to plug in x for 1 right off the bat, we would get an indeterminate form because both our numerator and denominator would be 0. So we can't use direct substitution. Instead, we need to figure out how we can get our typical trig limit identity, sine theta over theta, as theta goes to 0, to come out of this. So the first thing we want to do here is factor the denominator. So our numerator is going to be sine of x minus 1. That's not simplifiable. On the denominator, this can definitely be factored, though, and it becomes x minus 1 times x plus 2. So this is useful to us because if you notice, this part that I'm circling right here, sine of x minus 1 divided by x minus 1, this actually is our trig limit identity because since x is approaching 1, what we're taking the sine of and the denominator are both going to 0, and that's what we need to have in our regular limit identity, is that what you're taking the sine of and its denominator have to be equal, and those things have to be going to 0. So here's a good example of where it doesn't matter if the actual limit is going to 0. What matters is that what you're taking the sine of and what is on the denominator, that whole term is going to 0. And in this case, it does, because x is going to 1, so x minus 1 is going to 0. So this is our typical limit, and that's 1. So now we get that this problem simplifies to just 1 over x plus 2. And now we can use direct substitution because we don't have any thing that'll make it indeterminate. So when we plug in 1 for x, we get that our limit becomes 1/3. So just because your limit is not going to 0, that doesn't mean that you can't use your limit identity. In fact, oftentimes you'll still need to do that. It's that the term that you're taking the sine of and its denominator, not only do they have to be equal, but that whole term has to be going to 0, and in this case, that's how it worked out. And our last problem in problem number 10, another trig limit, but this one's going to look very different than the last couple because first of all, we have a limit that's going to infinity. And we also have a trig function divided by a polynomial. Now we have this in the last problem in part E, but that's where the limit was going to a finite number. Now we have an infinite limit. So this is going to change how we have to approach this problem. So you can see here that direct substitution or trying to compare degrees like we normally do with an infinite limit is not going to work here because we have a trig function in the numerator and a polynomial in the bottom. Also, when you have a trig function where the inside is going to infinity or negative infinity, sine or cosine going to infinity or negative infinity, we have a problem there because that is indeterminate, and that actually is something that can never be canceled out with another term because sine and cosine oscillate between 1 and negative 1. So as it goes to infinity, it just keeps going back and forth between 1 and negative 1. So this is completely indeterminate. So what you should think is whenever I have a trig function where the inside part is going to infinity, that's typically a squeeze theorem problem. So we did one of these earlier in this packet with a sine function where the inside was going to infinity and it was indeterminate. So this is actually the same thing, and we're going to use the squeeze theorem here also. So remember, when you use the squeeze theorem, you're going to take just the trig part and set up its standard inequality. The cosine of anything can only be in between 1 and negative 1. That is always true. And what we can do now is to make everything, or make the middle part look like our actual function here. We just need to divide all these terms by x squared minus 2x minus 3. So then we get negative 1 over x squared minus 2x minus 3 is less than or equal to our original function. And that's less than or equal to positive 1 over x squared minus 2x minus 3. So by just dividing all the terms, what we end up with is our original function in the middle, and we have now that it must be bounded by this on the lower side and this on the upper side. So now that's helpful to us because now when we apply this limit, even though we don't know what the limit of the center part is, we could figure out the limit of the left and right sides, and that's going to tell us what the middle one has to be. So you can see here, if we do an infinite limit of either the left or the right side here, this is just a rational function where the denominator would be going to infinity, but our numerator is a constant, 1 here, negative 1 here. Either way, if your degree on your denominator is bigger and you're doing an infinite limit, which is what the case is here, that limit is always 0. So we have a constant divided by infinity, or you can think of it as your degree on the numerator is bigger. Either way, that means these are going to 0. So that tells us that the left side here is 0, the right side here is 0. So if the limit at infinity here was 0, and the limit at infinity here was 0, that anything that's in between them as that limit goes to infinity, that must also be 0. So our limit here as x goes to infinity must be equal to 0.
The Teaching Center, UF's Learning Resource Center.